Let's now talk about how problem types, output units, and loss functions related to each other. So far, we have applied neural networks to binary and multi-class classification problems. The binary classification problems has two output values. We saw the examples of the perceptron and the XOR function using multi-layer networks. A common example of a binary classification method is if we want to do a medical diagnosis. We want to predict if a patient has a specific condition based on a number of input variables. And for multi-class classification, we saw the example of identifying which out of 10 handwritten digits were in an image. Another common problem that we haven't seen so far is a regression problem. Here we try to predict a numerical value rather than a class. We will look at how we can choose different networks to solve different types of problems. The type of problem that we want to solve will affect the type of the output unit and its loss function. Remember that the problem type guides what output unit and loss function to use. So we have already saw the binary classification. We can use a single output neuron using the sigmoid activation function. Given that the output of the sigmoid activation function is between 0 and 1, we can interpret this as a probability. We want to use the cross-entropy loss function together with the sigmoid function for binary classification, as you can see here in this figure. Moving to multi-class classification, we want to use softmax unit as the output unit. And we want to use the categorical cross-entropy loss function, and this is shown here in this figure. And finally, we have to solve the regression problem. So we want to use a linear activation function, and for the error function, we want to use mean squared error. Please note that in our discussion, we only apply to the output layer and the output units. The output unit type and loss function are chosen based on the problem type. However, the neurons in the hidden layers is a separate design choice. We will typically start with ReLU, and then based on experiment with other activation functions, we can decide to use other functions as needed. So this formula is the logistic sigmoid function, and this is the cross-entropy loss. This is the sigmoid function. As you can see, it ranges between 0 and 1. Now, the multi-class classification. Here we want the output layer to be able to have one output for each class. To do that, we use the softmax activation function. Each of the outputs will have a range between 0 and 1, but with an additional restriction that the sum of all of the output will total 1.0. That means we can then interpret these outputs as probabilities for the individual classes. For example, if output 1 equals 0.4 and output 2 equals to 0.6 and the others classes are close to 0, then we can say that it's a 40% probability that the object in the picture is of class 1 and a 60% probability of class 2. And the formula for the softmax unit is shown here. This figure shows a fully connected layer with a softmax activation function. And the bar chart here shows the effect that the softmax activation function will have in this case where the weighted sum are large, the blue bars. We see that the softmax activation scales the outputs down so that the sum of the output becomes 1.0. So when we work with a softmax activation function, we want to use the categorical cross-entropy loss function. This is a generalization of the binary cross-entropy loss function. If we would use softmax and cross-entropy in a case with just two classes, this will be equivalent to using a sigmoid neuron with a binary cross-entropy loss function. We use the term logit as the input to the activation function. Now let's talk about regression problem, where we want to predict a numerical value rather than a class. For example, we may try to predict the demand or the price of an item. In this case, we will use the linear activation function. The linear activation is actually the same thing as no activation function at all. The output is simply the weighted sum. This also means the output of this unit is unbounded and can be negative. So when we are solving a regression problem and are using the linear activation function, we want to use the mean squared error as the loss function. We saw that depending on what problem we were trying to solve, we would pick different loss function. This is to facilitate the learning process, but the loss functions are not necessarily intuitive to interpret. Therefore, it's common to also compute other metrics. These metrics will not be part of the learning process itself, but will give some intuition about the network behavior during learning. For example, the accuracy metric. If we are working with classification problem, we typically compute the accuracy metric, which tells us what percentage of the classifications are correct. For regression problems, accuracy is not that meaningful because it's very rare the predictions will be exactly correct. Instead, what we want to compute is the mean absolute error, which measures the average prediction error during training.